country and this part of the country, and the wonderful people that I have already had a chance to meet, and during this week maybe we'll meet more, sure. Now, before I start, I want to give you a very quick introduction to my part of the course, because then there is the part by Professor Fatah. Professor Sivarajee will share with you these two folders. Okay, I don't know if you can see them. I make them larger. Okay, the folder lectures and the folder MATLAB codes. Okay, the MATLAB codes are for the tutorials, and lectures are for the theory. Now, correctly, Professor Sivarajee said that I'm involved in a lot of applications that go from academia to industry, to the health institutions, okay, and so on. So that is true, but here I will give you the theoretical background. And then if you want to know about applications, well, you know, time is short, but apart from lectures, you can talk to me personally, okay? I will tell you a little more. Now, inside the lectures folder, there is this file, which I will open in a minute, with the first lecture. And then there are various other files, okay? They are not, they are more than you need, more than I can cover in the course. But I still wanted you to have this much, so you can go beyond what I have the time to tell while I'm lecturing. And some of these files are my handwritten notes, okay? So I apologize. I hope they are clear enough. Anyways, if anyone is interested in putting some parts of the handwritten notes into an electronic form and then share with me, that's okay. That will be much appreciated. But you don't have to do it. Okay, you don't have to do it. I'm just saying that some of these files are handwritten, and also they go beyond, okay, the scope of this. For instance, something like this. Okay, but okay, just to let you know. A number of other things are already in print. And there are a few papers. There are a few papers where the theory is explained, and there is also some application. For instance, very important applications these days are to climate. Okay? So response theory, which is what we are going to tell, using natural variability to predict forced response. In which field? In climate. Okay? What is happening to the Earth, which is one of the subjects in which I've been working for the past few years. Okay? And there are various other things. Okay? In the other folder, we will see it in the afternoon. Okay? In the afternoon, there will be a lecture there will be a 2 hours tutorial which has to do with the things. So let me start. Okay, this is 1 hour, right? So I set up the clock. No, not this one. View presentation. Okay, so here you see also my affiliations, which I have to acknowledge. Okay, so you see that I'm in the mathematics department of Polytechnic of Turin. I am in the physics department of University of Turin. I'm in the Italian National Institute for Nuclear Physics, and in Scienza Nuova, which is a new institution dealing with humanities and sciences together on the digital transition, artificial intelligence, which are very topical, as you know. Okay, And so this gives you also an idea of applications. Now, I will go fairly quickly through this file, again, because there is more than can be done in 1 hour. But I will highlight the main points, considering that also Professor Fataf will go into some of this of the subjects that I'm touching. Okay, so don't worry. However, if you have questions, you stop me at any time. Okay, don't be afraid. The purpose is not that I go through all the slides. In the afternoon, I will write at the board, okay, which is better for mathematics. But okay, this is to give you an idea that there are certain things, and each one of them would take a lot of time to investigate and to study. But it's better to know that certain things exist for those who don't already know, which maybe many of you will already know a lot of the things that I'm going to tell. So I just summarize some of the things that are important and that one could go deeper point by point. Then in the afternoon, I will start a more systematic kind of class with calculations at the board and so on. Okay? And so we make a pact. I try to do my best, but I know that I'm limited. So, if you like, the pact consists in you stop me when I'm not behaving properly. Okay? You tell me that you have difficulties and that you would like things to be explained better. Okay? Okay. So, first, the minimum of motivation. Okay? There are a lot of phenomena that we know how to treat, that we can predict very efficiently, and a lot of other phenomena that we don't know how to treat. For instance, astronomical phenomena have become quite easy, in quotes, for us to deal with. Just think of this. I don't know if you heard, but we have placed, we meaning humanity, a camera on a comet. Can you imagine that? Can you imagine that? A small spaceship was shot out out of the Earth. It bounced back various planets. It traveled for 11 years, just using our knowledge of gravity. It traveled by itself, okay, to meet a comet that was coming from the other side of the solar system on a given day at a given time. It reached that point, and then it dropped a camera on the comet, which was traveling at unimaginable speed. Okay? And this camera sent back pictures to the Earth. So now we know how a comet looks from inside. This means that we can predict very, very accurately, okay, tens of billions of kilometers traveled by the ship, by this camera. Rosetta is the name of the device, and Philly, the camera that was dropped down. Italian mathematicians even predicted that the camera hits the comet, and because gravity is too low, bounces and finishes into a region from which it is difficult to receive the light from the sun, and so batteries would expire. It all happened. It all happened. Okay? So, for certain things, we are pretty good. Well, these are far away phenomena, right? While we cannot predict in the same time phenomena that are close to us, like the climate, which is one of the subjects in which I work. one of the applications, okay? And for that, I work a lot with environmental engineers, for instance. So there are various kind of situations that we can meet. Some are those in which there are laws that are known to us. Newton's law of gravitation is what I just mentioned. Okay? There are situations in which laws probably exist, but they are not known to us. For instance, earthquakes. We know that the crust of the Earth has got a certain structure. We know quite a bit about that, and nevertheless, we are not able to predict an earthquake. Okay? Then there are situations in which probably laws don't even exist. And the financial market probably is one of those things. There are various opinions on this. Okay? Some people will say that, yes, there are the laws, but they are complicated. Other people will say, if there are the laws, then people would find a way of going against them, so in the end, they are not laws, and so on. Okay? I don't know. Now, in the mathematical description of these things, we have two main ways of proceeding. One is deterministic. You give me the initial condition, I tell you what happens after some time. Okay? And the other one is probabilistic. I cannot tell you where you will be after some time. I can give you the probability of you being somewhere after some time. Okay? In these classes, I will combine the two. Now, just to mention another application which is very popular, I should speak of artificial intelligence. I just give you the title, okay? But you can see the search for a pattern, for reconstructing a picture, or for finding out about, how to run an airport at a certain time of a certain day, where just the human brain is not fast enough to take the decisions that are. You can stick it in, yes, yes. For this thing, okay. Continue, is not identifying. So I just continue while it sets up. Yeah, but now, yeah, okay, let me see. Yes, perfect, thank you. So you can see it as a dynamical process. Okay? Here I have a slide on a model of guessing an unknown function f, starting from knowledge of it on a few points. Okay? And this function f could be whatever you like. Could be the picture of a cat, okay? Or could be the sequence of airplanes that have to land. Okay? Whatever you like. Well, you can cook up a dynamical model, a dynamical system in which the parameters that you will use to define the function have to converge through a certain rule that now I'm not going to explain, to a final object. The final object is our guess of the cat or of something else. Okay? So dynamics comes out even in here, and some of the things that I'm going to tell you, I'm not an expert of artificial intelligence, but I tell you there are experts of artificial intelligence who are using the tools that I have developed together with other colleagues, for instance, from Australia. Now, there are dynamics that are simple, but a lot of dynamics are very complex. In particular, they could be chaotic, which is one of the key words. Okay? They can be chaotic. They are characterized by what is called the butterfly effect, that trajectories diverge from each other exponentially fast. Okay? It means that if, for instance, I want to throw an arrow or a dart to a target, and I aim very, very precisely, okay, that it seems to point directly like this, well, in fact, I will have a little uncertainty in my aim. And this uncertainty will, at some point, explode so that I don't even know if I hit the target. Okay? This is something like chaos. But We'll say more about that. So to deal with this kind of situations, okay, there are various indicators, for instance, Lyapunov exponents. Okay, this poses some limits into doing what we would like to do with machine learning, or some time ago we called big data. Okay, learning from past, because you lose memory of the past. Sometimes having many parameters, rather than make it more difficult, it helps. Okay, but this is just to say. Okay, so this is for the introduction. Now, what do we say about dynamics? There are two kinds of dynamics that usually we look at. Okay, there are continuous dynamics. They are called flows. Okay, a flow is the solution of a differential equation. I will always have ordinary differential equations that are autonomous, no explicit dependence on time. That can be treated, but it becomes more difficult. Okay? So I have something like this, where my variable x, which could represent what? The temperature of the Earth in Jalandhar. The temperature in Jalandhar. Okay? It will follow a certain equation. In fact, they make predictions about what it will be tomorrow. Okay? Or it could be the position of the camera on the comet, or many other things. Okay? For notation, the solution, the flow, given a certain initial condition, time t, can be denoted like this. The initial condition and an operator phi t that evolves. And this phi t obeys properties of semi-group at least. Often it is a group. The phi t composed with phi s is phi t plus s. If you advance for a time t and then for a time s, is equal to advancing for the time t plus s. You may think that it's obvious, but not always. This is continuous evolution. Okay? Then you can, however, transform the continuous evolution into a discrete one by taking a section in space. You know that the trajectory comes like this. You put a surface, and you look when it hits the surface, and you get one point. Then the trajectory goes around, and hits in another point later on. Now, if you follow the points that are being hit by the trajectory, you will have a discrete dynamics, and you will have a different kind of mapping that at different times gives you the different positions. Okay? But discrete dynamics can be justified by itself. For instance, you find a lot of interesting websites about the logistic map. And here I listed a few of them. Okay? So you will have, when Professor Sivaragi will give you access to the folders, you have this kind of things. Okay? What is the logistic map? The logistic map is the simplest or the best known discrete dynamical system that jumps from point to point. Okay? It jumps according to a very simple rule. You have your point xn, and you want to know what it will be after one time step. It is defined in the interval 0, 1, so it is a number. It is a number. What is this number? It can be many things. Okay? For instance, if you rescale it with this, you can get to count the generations of rabbits that you can have in a factory. Okay? Put between 0 and 1, but then you expand, okay? And you get something like that, because they have an evolution that can be mimicked there. Or it could be the time intervals at which light is absorbed by our eyes. Okay? So it is something trivial, but not that much. Not that much. It is mathematically trivial. What is trivial? It is just a parabola, you see? Mu is a constant between 0 and 4. And x is a number between 0 and 1. So you draw between 0 and 1 a parabola. You take xn here, find the parabola, and you have xn plus 1. That is how it goes. This picture is for mu equal 3 and for 2 initial conditions. It is important to look at the rate of variations, which are the derivatives of this, and you will see what happens. Now, we call, for the dynamics, what is the simplest of trajectories? The simplest of trajectories is the one that does not move. It is called a fixed point, okay? So if x bar is a fixed point for a flow, it means that the function f, the vector field, is equal to 0, so that the evolution at any time t remains what it was. The next kind of object are the periodic orbits. Okay? The periodic orbits, they are not fixed. They are fixed after a certain time t, which is the period. So if you evolve for a certain time t, you go back to where you started. Fixed points and periodic orbits form what is called a set of critical elements, here indicated by gamma phi. Okay? And then there are points that are not fixed at all, and they are not even on a periodic orbit. They are called wandering points. Okay? What are the wandering points? Well, a point is wandering if it has a neighborhood ux such that, this is the definition, ux is the neighborhood of my point x. You start inside ux, and now you intersect the trajectory with the evolutions of this set u for all times larger than a certain time t0. Now, if the intersection between where you started and where you're going is empty, then it means you are wandering. You don't come back. Okay? These points form an open invariant set. What is an invariant set? An invariant set is a set that does not change under the application of the dynamics. Okay? And then there is another invariant set, which is the points that are not wandering, the other ones. Okay? If you belong to the wandering points, you stay in the wandering set. If you belong to the non-wandering set, then you will be points that violate this condition. There will be some time at which you come back. Okay? Now, among the invariant sets, you have also these ones. You have attracting sets. What are attracting sets? They are sets that, that you have if there exists a neighborhood U such that for every other set containing the one in question, okay, the evolution of U will end up inside V. So because this is for any V that contains A, it means you can squeeze as close as you like towards A. And in that sense, A then is attracting, because you start from outside and you end up as close as you like. Because it is an invariant set, for what I told you before, it means that if you start inside, you remain inside. If you start outside, you remain outside. You don't go inside the attracting set, but you get as close as you like. Okay? And then in that sense, it is called attracting. Then this set is called the fundamental neighborhood of A. Okay? Is the one that has to exist. The union of the evolutions of all these sets is called the basing of attraction. It is all the points that will end up as close as you like to A. Okay? An invariant set which is not attracting is called repelling. It doesn't want you to get close. Okay? And there is a very important property, which is topological transitivity, which links with what is called ergodicity. I will tell you a little bit about ergodicity in the coming classes. Okay? If there is a dense orbit in this set I, then the evolution is called topologically transitive. Dense means that you can go everywhere. That's why it is transitive. And that implies a property known as ergodicity, which we'll mention further down. Now, an important, very important theorem connected to these definitions is the Poincaré recurrence theorem. Okay? Suppose you have dynamics that preserves the volumes. What does it mean? It means that you take one set, you have to have a metric space, you have to be able to define volumes. Okay, you take one set, you evolve all the points of this set, the evolution will change the shape, but the volume will remain the same. Okay? The theorem is more general, but this is how Poincaré proved it in the early 1900s. Okay, so if you have a volume-preserving set, for flows, it means that the divergence of the vector field is 0. If any of you are familiar with hydrodynamics, then they will recognize that this is a condition of incompressibility of flows. Okay? And you can do it also in an abstract space, totally abstract. Okay? Say we are speaking about the temperature, or say we are speaking about the times of reaction of the eye to light. Okay? It's not a fluid, but you have equations that describe that. Okay? So if you have volume preserving, and D is an invariant bounded set, okay? Then for almost every x in D, almost every is a notion of real analysis. You may be familiar, but we speak of the volume, and so it is for the volume measure or the Lebesgue measure equal to 1, meaning you exclude a null set. For almost every x, you have that the lim-inf for time that goes to infinity of the evolution of x minus x goes 0, so points come close, okay, as time evolves. It means that you started at x, then you go around, round, round, but at some point you have to get back close. Note, it's not the limit, because it does not mean that you approach that point. But it means that in time, every now and then, you get even closer than you had before. So it is the lim-inf. Goes to 0. If you wait enough, you will get as close as you like. And then you wander around, but then you come back. Okay. And then there are other kinds of sets. I don't, okay? There is a whole list of sets. So, most important ones, or simplest to treat, are attractors, anti-attractors, and repellers. Okay? And they are called so. Did I say indecomposability? Yeah, well, indecomposability, it means that they are transitive. Okay? What I told you before, that you can go around everywhere. So you have these three situations. If you have indecomposable set, compact, when it is attracting, it is an attractor. When it is anti-attracting, if you go forward in time, you go away rather than. Okay? If you go backward in time, you get close. Okay? This means anti-attracting or repelling. Okay? The different basins of attractions are separated by other invariant sets that are called basins boundaries. They are at the boundary between different regions that attract, and so they are undecided, they remain there, okay, on the edge. A little bit to the left, they go left. A little bit to the right, they go right, and they are just precisely there. They are invariant sets. Now let's take a look at the logistic map, because for that it's possible to do very simple calculations. Okay? Here you see for mu equals 0.8, which is less than 1. Okay, you remember what was the definition of the logistic map? Do you have a marker? But otherwise, yeah, thank you very much. So, was x n plus 1 equals mu, yeah, xn 1 minus xn, okay? This is the map. So if mu is less than 1, the derivative of our parabola at 0 is lower than 1. So this straight line of slope 1 stays above. Now, if you want to follow the evolution, what will happen? You start from one point, okay, and you get to this other point. Now you are at this point, and you go and you get to this other point. And you see you are gradually converging towards the 0. But if you take mu bigger than 1, like mu equal 2, then you see that the situation is different. Okay, you start here, you go here, and then you go towards this other point. Now look, this point and this point are fixed points. Why? Because the map is equal to the point. Because this is the line y equals x. So y is equal to x. It means the point has not moved. Has not moved. So they are fixed points. You know the fixed points of a map of the interval. You look where they intersect the line of slope 1. Okay. Now you can compute what the fixed points are. Okay. Given that equation there, x equals 0 is always a fixed point because the straight line and the parabola always meet at that point. Okay. But then, when mu is sufficiently large, okay, there is another fixed point, which is 1 minus 1 over mu. That arises only for mu bigger than 1. Because if mu is less than 1, you get something negative. And negative is outside of your space. You cannot reach anything that is negative. Because the parabola maps everything between 0 and 1. Okay? So you need to have mu bigger than 1. If mu is bigger than 1, you have two fixed points. Okay? What has happened is this. This axis is mu. Okay? This axis is mu. For mu below 1, you only have 0 as a fixed point. 0. Okay? But when you cross the value of 1, mu equals 0 remains. But then there is the new other point that you see has got this shape. Okay? What happens in addition? It happens that as long as mu is less than 1, the derivative of the function at 0 is less than 1. And that derivative being less than 1 produces the picture that I've shown you earlier. Okay? That you converge to 0. But if the derivative is larger than 1, you converge to the other point. So derivative being equal to 1 makes a difference. Okay? It's called a bifurcation. You go from one point to 2 points. In this case, it's called transcritical bifurcation. I'll give you very rapidly. Okay? Just on bifurcations, you will need a course of 100 hours. But it's good to see what they are. A few bifurcations. What corresponds to? Corresponds to the variation of the numbers of fixed points or of periodic orbits. You can consider a periodic orbit as a fixed point of a different dynamical system. Okay? In the case of this, call this f of xn, then the fixed point is x are the points that verify this. You apply f and you don't change. Okay? But you can do something more. Suppose that you have a point x0 that goes into a point x1 that goes into a point x0 again by applying the map f twice. Well, then what you have is that f applied 2 times does not mean raised to the second power. Okay? It means iterate twice, f squared of x equals x. Whoa, f squared is another map. F of x equal x. So the periodic orbits of period 2 can be seen as fixed points of a different map. Okay? So speaking of fixed points is good enough to speak also of periodic orbits under many respects. Now here as I told you, there is a parallel between discrete and continuous dynamics, so I give you some examples of continuous dynamics. The first one, and I show you also only those that are called codimension 1 bifurcations, okay? That means there is only one parameter that produces the bifurcation, okay? So, for instance, if you have an equation like this, u dot equal mu minus u squared, okay, you will see that for mu less than 0, there are no fixed points, because this is a flow. You should have u dot equal 0, but if mu is negative, you cannot solve this equation equal to 0. Okay, so you start from any point and the equation pushes you down. Now you change mu, you come to mu equals 0, you can have at least one solution, u equals 0. And if you move further, you have two solutions. So for mu equals 0, only one fixed point. For mu bigger than 0, two fixed points. And you see which ones you converge to and which ones you go away from. This is a saddle node bifurcation, as it is called. This is the transcritical bifurcation, which corresponds to the passage from one fixed point of the logistic map to two fixed points. The pitchfork bifurcation, we will see it again. What happens here? You start from having a single fixed point, then you come to a value of the parameter at which two arise, okay? Or you go from two to a single one, okay? Pitchfork because of the shape of this thing, okay? Hopf bifurcation is very important. You know, a very, very, very famous neuroscientist from Rockefeller University asked me to discuss a problem about transmission of signals in the so-called tip links, which are tiny objects connecting the cilia in the ear that transform a mechanical signal into an electrical signal, where he has already found that there is a phenomenon corresponding to a Hopf bifurcation. Of course, he's a neuroscientist, not a mathematician or not even a physicist, although he knows a lot of mathematics and a lot of physics. Okay, I don't want to spend too much time on these things, I told you. But you see, the situation is like this. You have trajectories that spiral in to a fixed point. Now you change the parameter, and these trajectories don't spiral in anymore. They may start to spiraling outside. And you go from fixed point to periodic orbits that can be either approached or moved away from. So, for the logistic map, you have something of that sort. Okay? You remember that for mu bigger than 1, you have this second fixed point. Now, if you continue to change mu, you arrive to this point, where this fixed point continues to exist but becomes repelling. Like this one continues to exist but became repelling. And when this fixed point becomes repelling, two new points become attracting, and these 2 points belong to a single orbit. If you start here, you jump here, and when you are here, you jump back to that. Okay? And you see that you have drawn a pitchfork. And the points remain throughout, but they have doubled in number. Okay? Period 1 turns into period 2. And that happens for the logistic map. You can compute exactly. Okay? When do you have two solutions of the twice iterated map? Okay? You solve this little equation. And you find out that you have to be larger than 3. Because for mu smaller than 3, this is imaginary, it is complex, it is not a solution. How does this thing come? Let me show you in pictures. Because sometimes pictures help more than the mathematics, sometimes the mathematics helps more than the pictures. It depends. put together, they work much better. So this is F2, okay? This is F2. F1 is a parabola. F2 is a curve of degree 4, because you apply the parabola twice, okay? So it has degree 4. Now, it looks like a parabola that is a little more flat. This is 0.9, like I gave you earlier. It was a little higher. What happens if I increase mu? Well, if I increase mu, you see the shape of the parabola starts to change. It starts to do this. Why? Because degree 4 means it must come to a point of having 4 solutions. Well, to have 4 solutions, you have to have some bumps. At mu equal 2.5, you still have only 2 intersections. The 0, which is also period 2, because you go from 0 to 0 and to 0 again. And that fixed point, 1 minus 1 over mu. Still a fixed point, you go from it to itself and to itself again. But you can see that if you do it again, see what happens? It happens that at mu equal 3, the point where other orbits are coming, the map and the straight line become tangent to each other. Now here you can say that you have 2 coinciding solutions. Okay? And if you go further, they split. So the fixed point remains. But now you have 2 new points, and these 2 are not fixed points. They are fixed points for the twice iterated map. So these are points of a single periodic orbit. Okay? That is how it happens with the mathematics. And you see that it is crucial the step at which the derivative becomes 1. Okay? Which is what I showed you before. Now, at 1, the fixed point becomes unstable, repelling, and the orbit that is born arises as an attracting orbit of period 2. Okay? In fact, you can quantify these kind of things by looking at what iterations do. Okay? If I have a point x hat, okay, I ask if after the application of the map of a point to a point that is close to x, not exactly, you add a little h. Okay? Will the distance between the two, x plus h and x, initially the distance is only h. Okay? If I apply the map, will the distance be larger or smaller? Okay? So suppose that it is larger the initial distance, so you go to a shorter distance, you are converging somehow. Okay? I don't know why I wrote this twice. Because this is a fixed point, so it is equal, x hat is equal to f of x hat. Okay? Well, look at what you have written. Divide by h. There you get 1. You get 1 larger than the absolute value of this. Wow, but this, for small h, is the derivative with an absolute value. So 1 and minus 1 play the same role. If you want things to get closer, you have to have the derivative smaller than 1. Okay? And now you can repeat for n iterations, which will apply to orbits of period n. Okay? You can repeat. But now, the derivative of f of n, what is fn? Fn is equal to f composed with f, composed with f, n times. So it is a function of a function of a function. You apply the chain rule, and you have the rule. Now, the map is Fn. 1 has to be larger. If you want to converge to an orbit of period n, you need the derivative, which is this chain rule, smaller than 1 in absolute value. Here, sorry, I didn't put the absolute value. Okay, and that is what is not very difficult. It is the derivative in the first point times the derivative in the second point times the derivative up to the derivative in the last point. So you only have to do derivatives and follow the trajectory. Okay, and then things can become very complicated. Then you have situations with different kind of bifurcation, saddle node, in which you don't double the number of points. But for instance, you produce an orbit of period 3. And these two orbits make, and in fact, it's not a single orbit. They are two orbits that are quite close to each other, almost overlapping, but one is attracting and the other one is repelling. So you still have an even number of points, which makes 6, but is not a multiple of 2. Sorry, is not a power of 2. Okay? And this is, you may have seen this many times. Okay? It is the whole thing. When you reach 4, you have infinitely many orbits of all periods. Plus, they are a countable set, plus an uncountable set of orbits that are not periodic. And that is fully chaotic region. Okay? One-dimensional objects, of course, are very simple. Usually you have many more dimensions. The next step out of 1 is 2. And with 2, you already see a lot of things. With 2, for instance, you can define stable and unstable manifolds. They are not guaranteed to exist for all dynamical systems. It depends on the properties of the dynamical systems. Okay? But you can define a local stable manifold. S is for stable, loc for local. It is a property of the point x0, which is all the sets in our space, such that if you go forward in time, the point x0 and the other points in the set get closer to each other. Okay? This does not need to be a fixed point. Okay? It moves. X0 moves in time. But it brings with itself the other points that get closer and closer. Okay? For instance, this could be a periodic point. It goes around. It doesn't stay fixed. And then you will have other points that chase x0. Okay? Unstable manifold is when the two get close, but going backward in time. So locally and for a short time, they move apart from each other. Why do you define it for going backward in time? You say they get close going backward in time, rather than say they get far apart going forward in time. Because your space, I went through quickly, but typically is compact, bounded, okay? And then you cannot move apart forever because you will reach the boundary of the space. So it is misleading to think that the points get far away from each other. Also because there is recurrence. So points sooner or later will come back closer to where they were. Okay? But if you go backward in time, they can get as close as you want. So this is the unstable manifold. Local, because they're based on a point. Global, when you take the union, okay, of all the local ones. These are very important for chaos. Okay? These are very important for chaos. The clearest notion of chaos is that of hyperbolic dynamics. Now look, hyperbolic here is not the same, is not in the same sense of PDEs. Those of you who work with partial differential equations know that there are hyperbolic, parabolic, elliptic kind of PDEs. No, this is a different thing. It's related to the fact that trajectories draw kind of hyperbola. Okay, the trajectories do things like this. Okay? It is in this sense. How come? Okay, you take an invariant set, say I. It is called hyperbolic if for every point in it, the tangent space of at x in your space M can be split in 3 linear spaces, which correspond to unstable trajectories, neutral trajectories, and stable trajectories. What are they? There should exist a constant k bigger than 0, and another constant c that depends on 2 points on the space, the point of interest, x, and the other points in the set, okay, that are both positive and continuous. This one is positive and continuous. And they verify this for every x in the invariant set and for every time bigger than 0, for every vector in the stable space and for every vector in the unstable space, what does happen? It happens that the evolution, this M, is the evolution in the tangent space, okay, of the stable vectors gets smaller and smaller in size. In fact, it gets exponentially smaller, okay, than the initial size. In the unstable space, the vectors become exponentially larger. Plus gamma is the angle between stable and unstable. This angle should remain bounded away from 0. So it is called hyperbolic if you have a structure like this of the dynamics. This is your x. X, yes. And these are any other x prime. Okay? If around this x the moves, but brings with itself all the other points, trajectories goes like that. They approach and then they go away. This is the stable space. This is the unstable space. Okay? And it is important that these two spaces have an angle, gamma, that never goes below a certain value. Because stable and unstable manifolds should not get confused. It is also quite contradictory because on one hand you want to expand exponentially fast, in the other side you want to contract exponentially fast, so you have to avoid that. But if you have this situation, okay, then dynamics are really exceedingly complex, and you can call them chaotic. A characterization of chaoticity in whatever number of dimension is given by the so-called Lyapunov exponents. Okay? I'll give you the Lyapunov exponents later. But basically, the precise definition. But basically, the Lyapunov exponents are the rates of expansion when they are positive, e to the lambda t, lambda bigger than 0, belongs to the unstable manifold, e to the, let me call it, well, let's say lambda I, and then lambda j, e to lambda jt, for lambda j less than 0, that corresponds to the stable directions. If you have that hyperbolic structure, what happens is this, is that the positive exponents are separated, apart from one that could be 0, apart 1, okay, they are separated by a value k from the negative exponents. That comes from the hyperbolic structure. Okay? So what you can have is a certain number of positive exponents, bound k. Okay? Larger than, forget about this, which is present in flows, not present in maps. Okay? The next step is the negative ones are smaller than minus k. So there is a positive distance between positive and negative exponents. That causes a lot of chaos. Okay, maybe I have a picture at some point. Well, this is for the logistic map to show you that you can easily compute the Lyapunov exponents. Okay, because you remember you have just to compute the derivatives. And it is easy to see that distances near a fixed point contract exponentially with the parameter mu, and you can write this mu to the n as lambda e to the lambda n, and that will be your lambda. Okay, now depending on where you are, this lambda will be negative or positive. If it is negative, you're speaking about a stable orbit. If it is positive, you are speaking of a non-stable orbit. In the logistic map, you even have a situation in which lambda goes to minus infinity, and that is called superstable. In one iteration, you go from 1 to 0 in one go. Okay? If somehow you reach 1, you put 1 here, the next point is 0, and you don't move anymore. It is super stable, because more stable than that is impossible. Let's see what happens if we change the parameter. Here it is called R. Sorry, but this R is the mu. And in red you see the trajectories, right? So for R equal 1, this fixed point is still attracting, but just marginally, because parabola and straight line have become tangent here. The derivative is 1, so you are in a marginal situation. Now let's see what happens to the trajectories starting from the same point as I increase R, okay? You see? We are in the situation, let me go back a little, in which there is a single point that attracts. It is this one. It is the one that was called 1 minus 1 over mu, or the R. Okay? But if I go a little further, you see this is 248. Remember that something happens at 3. What? Got stuck? It goes back. Ah, yes. Okay. You see? You have created periodic orbit. Now you go around. Okay? But these periodic orbits now at 318, maybe they're not stable anymore already. Okay? In fact, you see, these are the period 3 orbits that I showed you earlier. Okay? And if you continue, it becomes very chaotic. Okay? This I will skip. This is the slide of indecomposability. Never mind, I skip it, okay, because there is a lot. I just want to show you what happens. How come that you can, one way of producing very complex dynamics, okay, are the so-called homoclinic and heteroclinic intersections. What are they? They are intersections of stable and unstable manifolds of a single point, homoclinic, or of 2 points, heteroclinic. So what you can have is a situation like this, for instance. This perhaps is simpler. You have a fixed point which has one unstable manifold, this one. If you sit in this direction, you will move away from the point. And a stable manifold, okay? The point is fixed. So points on the green line, either they get close or they move away. But remember that the space is bounded, is compact, and so they cannot go too much away from the point. We'll come back at some stage. So along this path, you find points that move away, and when you come here, you find points that move toward. Now look, they don't follow this trajectory. Okay, they don't follow this trajectory. This is the set of points that eventually gets closer or further away. They don't follow this trajectory if you have hyperbolicity, because if I sit here, I will move transversally to that. I will do this kind of complicated shape. Let me see. Yeah, this is the fixed point. You will do, try to think of this picture, okay? You will do this kind of oscillations around the stable and the unstable manifold. Now you see what happens. It happens that if you are on the stable direction, say you are in this point, the next step takes you down here. Then you turn around and you have got closer. Then you go around and you have to get closer. Why? Because you were in the stable manifold. So you want to get closer, eventually closer. But as you get closer, you do this kind of wrinkles. Now, because of this, as you go down this direction, you start to become parallel to the unstable manifold. While you get closer through the stable manifold, you get further away through the unstable manifold. And so in one direction you get closer, in the other direction you get far away, and you can imagine that these lines here becomes dense and extremely long. And what does that mean? It means that you cannot predict what will happen. Because this is the point, the fixed point. And these are the many trajectories that I don't draw all of them. Now they accumulate close to this point. They will become infinitely many. Infinitely many. Now, when I do an observation, I do the observation with a limited accuracy. So I don't know if I am in this one or if I am in this one. Okay, so say I have a little uncertainty like this. Imagine that this can be as small as you like, because before you reach this point, you have gone back and forth infinitely many times. So you say, am I here, or am I here, or am I here? Because if I'm here, I will move in this direction. And if I'm just a tiny bit moved apart, I will move in this direction. Where do I go? I don't know. That is chaos. Okay? It is one way of producing chaos. It's not the only one. Okay? Now I have a list of possible models that you can study in the tutorial. I just show you quickly because the hour is about to finish. Just to show you, here it is explained about their bifurcations, attractors, and so on. Okay? And in the lecture of the afternoon, I'll tell you about invariant measures, which here are computed for the logistic map. Okay, so at this point, you will find the analytical expressions for the simple case of the logistic map that can be computed, everything analytically. In the afternoon, I give you the general theory. Okay, so this we can skip because you just go, and when you are in the tutorial you do these things. I just want to tell you two things very quickly, to which we can go back whenever you like. So, because of this impossibility to make a prediction, even if the dynamics is totally deterministic, right? You understand that this is totally deterministic. There is no uncertainty in this expression. But the uncertainty is in our ability to follow where these dynamics will go. The dynamics will go where it has to go, but we don't know. Okay? There is difference between the phenomenon and what we understand of the phenomenon. Okay, so because of this, our own uncertainties, we will do better to use probabilities. That I explain in the afternoon. But the term that I call ergodic, to which we return, has got to do with this. That if I do a time average of a certain quantity along a given trajectory. This bar means I average in time. What does it mean? I divide by the time and sum over all what I observe along the trajectory in time. So this is time average. The time average becomes equal to an average with respect to a given probability. When you can do that, the dynamics will be called ergodic. Okay, this is one thing. The other thing, which I'm not going to do, but in the slides you find done for the logistic map, and then the handwritten notes for the Baker map. The Baker map is a bit more complex, but also gives much more satisfaction. Okay, the idea is this, is that because, how can you quantify this loss of determinism in favor of probability? Well, for certain maps, which are isomorphic to Bernoulli schemes, for those of you who know about stochastic processes, otherwise don't worry, Bernoulli schemes are extremely stochastic systems, okay? What you can see is something like this, is that you give me an initial condition between 0 and 1 with a number of digits. If these are expressed in binary language, okay, in binary, not in decimal language, then the evolution of the logistic map can be transformed into an operator which is very common in functional analysis, which is the shift to the left. You go from a number to a sequence of symbols where the AI are equal to 0 and 1 only. And you know what is one iteration? One iteration means erasing one symbol and shifting to the left. Very simple for very complicated dynamics. If the dynamics are not sufficiently complicated, this does not happen. Okay? The isomorphism does not happen. You want something exceedingly chaotic. But if it is exceedingly chaotic, you can transform the dynamics in shifting the digits. But now suppose you know the position of your point with 100 digits. And from the 101, you don't know what you have. After 100 steps, you don't know where you are. Okay? And with this, I stop. Thank you very much. And usually, you don't have 100 digits. Okay. Thank you very much. You didn't ask any questions, but I'm happy to answer now, although this morning we started a bit late, but I'm here for you.
So any questions from the participants? Feel free to ask. You are here to learn. If there is any questions from the participants.
Well, you look at the material. If you can make the two folders available, right?
Yes, yes.
Okay.
Thank you everyone. Yeah. So thank you everyone. So now hereafter I hope everyone you are having the schedule with you. We go exactly as per the schedule, and small request, Professor, you can please sit.
Yeah.
And the small request.
I can switch it off.
This is actually the live is going on, video recording. So it is a humble request that please don't move like this. If by chance for any reason you want to move, you go this way, and from the back side you go. And whatever the schedule is mentioned hereafter are the classes as well as the tutorials as well as the sessions will start very exactly. No more difference will be there. So 1 or 2 minutes or 5 minutes early, you please come and get settled. And for the lunch, I hope all the participants, please sit.
Yeah, but then this makes noise. I'm happy to stand. It doesn't bother me.
For the lunch, I hope you all know the girls, it is arranged in girls' hostel or guest house where you are given preference. And for the boys, it is arranged in the boys' hostel or guest house where you are given the preference. And for others, few of you like made own arrangements, you have 3 possibilities, either girls' hostel, your girls or boys' hostel, or the guest house, or these centers. And for any other reasons or anything, you can contact us for any time. And Like I hope you all are almost there with heavy winter jackets, everything to face the weather. And it is maybe a little bit different for others, those who come from different parts of India. But those who are around Punjab and the nearby states,
They know.
it might be very easy. You are handling regularly, and all the this course kit that you would have received. There were 5 participants. They did not receive the kit. Just now, after this, if you come with us, we will be giving you the course kit, and then the tutorial will happen over there. By chance, you could have come with your laptop, own laptop with MATLAB installed. You can use your own laptop. If you don't come with your own laptop, you can use our systems. In all the systems, MATLAB installed. So it is your choice whether you want to use your own laptop or the systems is your choice. So the tutorial will start at 10:30. But before that, we have one more lecture. The lecture started at 2:10. It is now actually 1:42. So only this time will please adjust. After that, everything will go as per the time. So please come. The lecture will start at 2:10. So please come by 2:10. You have about 30 minutes time.
Maybe for the first day we can delay a little the beginning, so there is time to eat something.
In the tea time, we will reduce. So yeah, lunch will be difficult. So 1:40, 2:30 is okay.
2:30 could be.
2:30.